Right, so as we get into the calculus portion of our class, you had some introduction to calculus yesterday that I posted on the calendar. I put a couple videos on there. I hope you watched them. They will help explain what you see in the first part of this. So I'm not going to go into too much depth. If you hopefully watch those videos, that would help you with the first part of this explanation, just to give you some background on how the calculus works and all that stuff. So that's what this first part is for, this first lesson. But the general idea is, if you can look at this curve right here that I'm tracing for x squared, if I want the slope, or the gradient as we call it in IB, or the instant rate of change at a specific point, how do we do that? So typically if you want the slope, you need 2 points. You got to do y minus y over x minus x, or what we would refer to as the change in y over the change in x, or delta y over delta x, as we'll start calling this dy dx, is where that comes from for this. So, but typically to use that you need 2 points. So the calculus comes in when I don't have 2 points. I only have 1 point. So how do we figure out the instant rate of change at a specific point? So as we get into the next part of this, one way of doing that is to use what we call the derivative of the function, which one way to get the derivative is this method that you see right here that we call the first principles method. So this is one way of doing it. You're going to find out, I'm going to save you a little trouble on this, you're going to find out there's a much easier way to do this. And so a lot of this is really used for introduction so that you can see where the derivative comes from. But for the most part, we're going to be using things called the power rule, the chain rule, and things like that. So this is just more introduction. So this still comes from the whole y minus y over x minus x setup. So if you think of f of x as a y value, right? So here's a y value, but if I did some y value minus another y value over x minus x, so x plus h minus x would just give me h for the denominator. So this still comes from the same slope formula that you've seen in the past. All you would have to do to get the derivative of this is just, so if you take a scenario like this one, if I want to get the derivative, which is that little point that you see right here, that little accent mark, is if I take this function and just use this formula. So for the first part, I'm going to replace x with x plus h. So as you see right here, I'm going to have x plus h squared. That's what goes into the first part. For the second part, you just keep the f of x. So I'm just going to keep x squared for the second part, and then this would always be over h. From here, all you do is simplify. So as I simplify all this, so I'm going to start by squaring x plus h, and that's going to give me this look here. Then I'm going to combine like terms by subtracting x squared, and that's going to get you this next line. And then if I divide h into every term, all I am left with is this. But keep in mind on this, if you caught what I said in some of the earlier videos about limits, right, this is referred to as the limit as h approaches 0. Well, as h approaches 0, as this becomes 0, all I would be left with is 2x. So 2x is the derivative of this function. And so that's using the first principles method. But now that you have the derivative, you can always use the word derivative synonymously with the word slope or gradient. So this now represents the gradient for every point on this function of x squared. So if I want to get the instant rate of change, or the slope or the gradient at a point where x equals 2, well, all I would have to do now is sub in a 2 for x, and I get the slope or the gradient at that specific point. Same thing here. If I wanted to say what is the instant rate of change, or what is the gradient where x equals 3, if I just sub in a 3 into my derivative, then I get the slope or the instant rate of change at that point. You're going to see in the next upcoming lessons the easier way to do a derivative instead of the first principles method is what we call the power rule. And the power rule simply says take your exponent, multiply it to the front, so I'm going to have 2x, and then subtract 1 from your exponent, and you get this here. And so that's going to be a quicker way of doing this, but you kind of got to go through this first step as sort of introduction to calculus. So same thing on this one. For the last two examples, it's just the same using the first principles method. So again, I'm going to start by replacing x with x plus h to get my first part of my setup here. So this would become x plus h to the fourth minus 2. And that gives me the first part of my setup. For the second part, you just keep the original. So you keep the f of x as the original. And then this is always over h. From here, you just simplify. So I got to do x plus h to the fourth power, then subtract 2, then subtract all this. And so if you went through all that scenario, so you got your expansion, you're going to combine like terms. That brings you all the way down to here. You have to notice that as you go to simplify all this, every term will have an h in it. That will always be the case, otherwise you did something wrong. Because the h will divide out of every term to get your derivative. So if I divide out the h from every term, I come all the way down with this guy right here. So that's our derivative. Again, what you're going to be doing with this and down the line is, instead of the first principles method, you're going to be doing the power rule, which again, if you did 4 times the front, so I got 4 in front, subtract 1 from your exponent, and you got 4x to the third. So that's, at least for now, that's a way of checking your answer to make sure that you did it right to get that derivative. But you can now find the gradient at any point on the curve. So if I want to know the gradient of the curve at that specific point, I plug in my x value. So if I plugged in a 2 for x right here, then I get the gradient at that point of the curve. One more example right here. So if you want to go through this one, take the same steps. Maybe try this one for practice before you read through it with the notes. But again, you would start by replacing your x's with x plus h. So I got negative 7 times x plus h squared plus 8 times x plus h. And so that's what you're seeing right here in the initial setup. After the minus sign, you do the original f of x scenario, all that over h. And as you go through and simplify, again, at one stage you have to get to a point where you notice h is in every term, and so we can divide out the h in order to get it all the way down to the end to get our derivative. So notice again, the term that contains h, as h approaches 0, so that should say h right there, as h becomes 0, so if I replace h with 0, what am I left with? I'm left with just negative 14x plus 8. So the same was true on this one. As h is approaching 0, if I actually replaced h with 0, this whole term would go away, that whole term would go away, and that whole term would go away, and I would only be left with the one term that doesn't have an h in it, and that's where you got your derivative on that. So once you find the derivative, you can now find the gradient at any point on the curve by plugging in an x value. So stick 4 in there, and you get the instant rate of change at that point.